of the current malware scanner, and there are many problems. So we try to fix that by proposing a new malware scanner for specifically work for virtual machine. So at first we introduce the concept of virtual machine, and after that we introduce architecture, design, and implementation of eKimono. And on this talk, I focus on Windows protection and focus on detecting rootkits inside virtual machine running Windows. And after that, I have some demo, so you can see that eKimono can really detect some malware. And conclusion. Okay, first part, the problem of the current malware scanner. So what is rootkit? Yeah, rootkits capture malware that they try to hide their existence in the system, and they can do many ways to try to hide themselves in the system. First of all, they can hook critical function in the system so they can hide their residence. They can patch system process. They can modify the import REST table, export REST table. They can do in like hook kicking, or they can modify the system kernel. They can modify system code, CDT table, IDT table, import REST, export REST, and they can modify kernel object inside the kernel. So on the current malware scanner, you can see that to detect the malware inside your system, usually you run the malware scanner inside your system. And there's one thing important. Mostly the current malware scanner only scans the hard disk to detect the malware. So you can see there are many problems. First of all, you can have rootkit inside your system. And because rootkits stay inside your system, so they can easily fool your rootkit scanner. They can return the fake information when the rootkit scanner queries information from this system. And especially if the malware running inside the kernel, you can see that it can even tamper with the malware scanner. It can kill the malware scanner. It can make the malware scanner so it doesn't work correctly anymore. So you can see that those problems are very serious and cannot be fixed in the design. There are the problems. You can see that mostly the malware scanner, they focus on scanning the hard disk only, but many of them ignore the memory. They don't scan the memory. So for those rootkit and malware that only stay in the memory, but never write them down to the hard disk, those malware cannot be detected by the current malware scanner. So that's another problem. So there are many problems. So I want to have better scanner. So want the new scanner that detect malware inside the memory. And it cannot be, it's not easy to fool my malware scanner. And the malware cannot, or it's very hard to attack my malware scanner, even if the malware running inside the kernel. So I dream to have a malware scanner that has those three features. Yeah, so the next part I focus on introducing my malware scanner that satisfies those requirements. Yeah, so I build my malware scanner for virtual machine. So here's a virtual machine concept. You can see that basically the virtual machine allows you to run multiple operating system at the same time in one physical machine. And in the virtual machine concept, they actually classify virtual machine into two types. The first one is host virtual machine, and the second one is guest virtual machine. And remember that the host virtual machine control all the other guest virtual machine. And that is a very simple diagram of the virtual machine concept. So how about Zen? Zen is the one open source virtual machine, and they, of course, they have the same concept. So in Zen, host VM is called domain 0, and the guest VM is called domain U. And from domain 0, we control all the other domain U. You can start the guest virtual machine, stop virtual machine, you can do anything with them from domain 0 in Zen. How about QEMU? QEMU is similar, but here the guest virtual machine is run as a process inside a QEMU process. And the QEMU process runs the guest OS inside the host operating system. KVM is similar, but you can see here that KVM in the KVM case, they accelerate the virtual machine by employing one kernel layer named KVM, and this kernel layer exploits the features introduced by CPUs that has virtualization technology. So the KVM virtual machine is much faster than the QEMU virtual machine. So we need the hardware here. Okay, so how about manage those virtual machines? And recently, people proposed a framework named Liver, and Liver is kind of unified framework that can be used to manage their own kind of virtual machine. And you can see that it supports Zen, KVM, QEMU, VirtualBox, VMware, and so on. And you can see that Liver is kind of framework, and on top of framework, you build application. And application can use a Liver framework to access to those virtual machines, run as a lower layer. Okay, so how about eKimono? The idea of eKimono is very simple. I put the eKimono, which is a malware scanner, I put the eKimono inside the host virtual machine. And from here, my eKimono run on the host virtual machine and access to the memory of the guest virtual machine. And from outside, from the host virtual machine, you can scan the memory of the guest virtual machine to detect the malware inside the memory. And from outside, you can also manipulate the memory. You can write to the memory. So you can, for example, you can disable the malware inside the memory. So here's the architecture. It's very simple. You run the scanner inside the host virtual machine. And from here, the scanner access to the memory of the guest virtual machine, and we can detect the malware. And we can do that because all the virtual machine should provide interface. So from the host virtual machine, you can access to the memory of the guest virtual machine. So that is feasible. That's doable. So you can see that my design for the malware scanner satisfy all the dream requirement. My malware scanner deals with the memory resident malware because it scans the memory, right? Second, from outside, you can get the correct information even if the malware runs in the kernel of the virtual machine. I can show you how I can do that later. Because basically, I don't rely on the OS of the virtual machine to get the information. So I cannot be fooled by the malware. And third, because my malware scanner runs outside, so the malware inside the virtual machine cannot attack it. It's in the design. It cannot attack my malware scanner. And there's even some more benefit. For example, my malware scanner is invisible to malware. From inside, it cannot know that it's being monitored by the malware scanner from outside. And from outside, it can effectively disable the malware running inside the guest VM. So we have many advantages for this design. However, there are many challenges. The biggest challenge is that from outside, you can see the memory of the guest virtual machine. But what you can see is only the raw memory. you see the first page of the memory, second page of the memory, third page of the memory, but you don't know in detail about what is inside the memory. You only see the raw memory. So our job is that we have to analyze the raw memory to understand the context inside the memory. So there are two challenges. First, because you want to understand the memory, so you have to understand the virtual memory, virtual arrest. Everything inside the system is about virtual arrest, not physical arrest. So we have to enable that we only have access to the physical memory from outside, but you have to understand the virtual memory. That is the first problem. Second one, after you can access to the virtual memory, you have to analyze the virtual memory to extract out the OS semantic object from inside the virtual memory. And of course, the second part, we need very good understanding on the OS internet, so we can extract the correct information. So we have two challenges, understanding the memory and how to get the OS object from the memory. So to solve those two problems, I propose two frameworks. Anidor framework can be used to understand the virtual memory, and eKimono framework can be used to get from the memory the OS semantic object. And here's the architecture. At the bottom layer is a framework named Anidor. Anidor can be used to access to the memory of the virtual machine. eKimono framework will extract from the memory after we have understanding of the virtual memory, the object inside the memory. And after that, the top layer, eKimono, is application built on top of those two frameworks, and eKimono will get the object inside the memory and analyze them, process them, and try to detect the malware inside the memory. And that is the full architecture. So now I will go into the detail of each framework. The bottom layer, Anidor, you can see the framework here. I split Anidor into multiple layers, so it's very flexible. And actually here I designed the Anidor so it works thanks to a plugin interface. And each virtual machine want to be supported by Anidor will be built as one plugin. So you can see that we have plugin for Zen, for Libert. Libert support own kind virtual machine. So if you support Libert, you can support own kind virtual machine and VMware as well. And the middle layer will, thanks to the bottom layer, which provides access to the physical memory, the middle layer will provide access to the virtual memory. And on top of that, we have some optimization enhancement. So you can speed up the process to convert virtual memory to physical memory. So here you can see that it basically it doesn't depend on OS. It supports own kind of OS run inside the virtual machine, and it doesn't depend on the hypervisor. We support Zen, KVM, and QEMU so far. VMware can be supported, and you can see that Anidor play a role like software MMU. So it can convert from the virtual memory to the physical memory. And besides, Anidor also provides access to the register of the virtual machine. Yeah, so here's Zen. Anidor supports Zen, and we implement the Zen plugin for the Anidor, the bottom layer over there. How about Libert? Well, you can see that originally, Libert has no interface to access to the physical memory of the virtual machine. So to build the plugin for Libert, I had to patch the Libert, and I submitted the patch to access to physical memory to virtual machine to the Libert project, and they already merged it into Libert 0.7 from August. That means now Anidor support Libert out of the box if you use Libert 0.7. So here's my patch submitted to the Libert project. How about VMware? Well, unfortunately, we cannot support VMware now because to build the plugin for VMware, VMware give me access to physical memory. But that's exactly what provided by VM Shape API in VMware, but VMware they don't open the VM Shape API, so I cannot do anything here. But in the future, if they open the VM Shape API, I can support VMware in my framework. Here's some ShapeOn API. You can see that I want function to read the memory, read the virtual memory in the user space. I can write to the virtual memory. I can read the physical memory. I can write to physical memory. So those functions can be used to access to the virtual memory and physical memory inside the virtual machine. Okay, that's the first challenge. I can access to the memory now. Now I need to get the object from inside the memory. So to get to the object inside the memory, I have another framework named eKimono. And eKimono framework built on top of AnyDoor. And AnyDoor provides the memory access to eKimono. And eKimono uses memory access provided by AnyDoor to access to memory. And after that, it extracts out the objects, system object from the memory. So here, because we want to focus on detecting malware, so we focus on important object that can disclose the residence of malware inside the memory. So we can first focus on things like network port, connection, processes, kernel module, those things you want to get out from the memory by this framework. So here's the architecture eKimono. You can see that I also split the eKimono into multiple layers. Bottom layer, middle layer, and top layer. So I explain why I need those layers. So to extract the object from the memory, you have two things to do. First, you have to locate the object where it stays in the memory. Second, you need to extract the sub-fin from the object. Here's one example. So you can focus on those objects, and you need to locate the kernel module in the memory, processes in the memory, system handle, open file, resist, DNN file, open by processes, network connection, network port, driver, and so on. So to locate those objects in the memory, actually I don't do anything new here, because already in the community, there are already many research already done about how to locate those objects. So I don't do anything new here. I just use already published research, and I just implement my framework here. Now, after you can already locate the object, you need to extract fin from the object. So for example, you can locate the e-process object which keep all the information about each process in the memory. Now, you want to know the create time of this object. So you want to get the extract out the third field, right? Create time. So to do that, you need to know that create time stays at the offset 70, and create time has a size 8 byte, right? You want to know exactly where it stays in the object. But the problem is that those fields can change between Windows versions. They're not fixed. So between Windows versions, they can move fields around. And they move around very often. Or they can even insert a new field between. So those offset change all the time between Windows versions. So that's one problem. How can we access to those objects independently of Windows version? So there are already many research now. They want to do the same thing. But how they do that? They hard code on the popular object in the program. And they hard code the offset and the size of the object members that they want to extract out from the object. So everybody does the same thing. But you can see that's not enough. Why? Because by hard code those objects and offset those interested members in the program, you can access to only to those objects, but not the other objects, right? So that's limited to the program. So I have another rim. because you want to get to own the object and own the member inside each object independently of Windows version. So I want another framework that support all type of Windows, all type of OS actually. And I want to do that on demand at runtime, not at compile time. And it can answer many questions. What is the size of each object? What is the offset of this member field in this object? What is the size of this member in this object? And so on. So yeah, here I have another framework, latent framework named libdi. And it's, libdi rely on public information on OS object. I don't involve with Microsoft, so I have no internal information about those objects, but I rely on public information. And now we support OS like Windows and Linux. And how to get those information? I build those objects in debugging format, and after that, I extract all those information from the debugging information. So here's how I support the Windows. I rely on React OS. Anybody here know React OS? Yes, very nice. Everyone. React OS is open source project that try to build Windows but with open source. You have the source code. So the idea is that you have Windows application. So normally you have to buy Windows OS to run application on that, right? But the React OS is open source Windows. So you can run your application inside the React OS without having to buy Windows. And that's the idea. React OS is free and open, support from Windows 2003 and up. So I compile the React OS file header with the debugging information. You can see that I use a Z++ compiler. Using debugging information, I compile my object file. And after that, each Windows version has one object file. Windows XP, Windows 2003, Windows Vista, Windows 2008, Windows 7, and so on. Each Windows has one object file like that. So there's one problem, some problems. React OS only support Windows 2003 and up, so actually I had to patch those headers to support Windows XP and previous version. And I fixed many incorrect information in the header React OS, and also had to patch to support the recent OS like Windows 7. React OS haven't supported them yet. So here's a simple API for libdi. You can use the first function to get the size of the structure. You can use the second function to get the size of the member in the structure. Third function to get the offset of the member in a structure. Here's the sample. I want to get information on Windows XP, so I have one function to open Windows XP object, Windows XP service factory, and you can see the DI struct size return the size of process structure. The next function return the member size, the create time member inside each structure. And the last one returns the offset of the create time in the process. So you can see that the same code can work with all the Windows version as long as you open the correct Windows object file. It can be Windows XP, Windows 2003, Windows Vista, Windows 7, and so on. So the main code doesn't change. Okay, so you and I, we have some API, so you and I can get into the memory and extract out the object. You can extract the first object in the list object. After that, you return the next object in the list, and so on. Here's some simple API. You can, first of all, you can use the first function to get the first process in the list of all the processes in the memory. It's very simple. After that, you want to get the next process in the list of processes. And in case there are still processes, you call the get task next again and again until you get all the processes in the memory. You can also get the process ID. You can get the first DNA file opened by one process And in case that file, that process open many DNA file, you can repeatedly call the last function to get all the DNA file opened by that process. So here is the architecture of eKimono again. Bottom layer provides the information about every object in the system. So, and now we support Windows object and Linux object on Windows version. And the top layer use the information provided by the bottom layer, and it comes to the memory, extract out everything you want to have. Kernel module, process, its DNN file, and so on. Here's the architecture again. Bottom layer provides access to the memory. It can be either virtual memory or physical memory in the virtual machine. The middle layer gives you every object inside the memory you want to have. The top layer is operation built on top of choose framework, and it gets all the objects inside the memory and process, analyze, and it can try to detect the malware inside the memory. There's some other advantage of eKimono. You can see that eKimono requires absolutely no support from the protected virtual machine. We don't install any agent inside the guest virtual machine. We just run the scanner outside, that's all. We never change anything inside the guest memory, in the guest virtual machine. Don't install anything. So we have zero cost deployment. Just run outside, that's all. It's very simple and easy. Yeah, so you can see here, eKimono is a service provided by eKimono, and we perform many methods to detect the malware inside the memory. Baseline, cross view, black and white, disk checking, abnormal behavior detection, and so on. About baseline detection, it's very simple. The idea is that at the time when we know that the system is clean, we create the baseline. And after that, when you want to detect the malware, you run the scanner and get all the objects from the memory and compare them to the baseline. If we see something not in the baseline, we report, because that can be the malware. So it can be the kernel module, system call, processes, and so on. Those things not in the baseline will be reported. Cross-view detection. Yeah. Cross-view detection is another way. Basically, it's very simple. Now we have rootkit inside the virtual machine that try to modify something so they can be hidden from the system. But actually, each thing can be seen from many views. So because the rootkit is not perfect, it modifies something and you don't see that anymore. First of all, it tries to hide the process in the memory. So it maybe try to modify the process list so it don't see the hidden process anymore. But there are probably many ways to see the list of the processes in the memory. So if you see the list of processes from many views, you can see different things. So it's a clean system. If you see things from different views, you see the same thing. But the rootkit is not perfect. So when you compare the different views, you might see different things. So that is the idea of the cross-view detection. So we compare objects from different views. So here you can try to detect hidden processes, hidden thread, hidden DNN, kernel module, network connection, and report. If we see something different in the different view, we can report, and that can be malware. Did I speak too fast? Okay, the next method, blacklist and whitelist checking. Well, the idea is very simple. Blacklist detection is that if you see something not in the blacklist, you can immediately report that will be something bad. For example, if you see if you list all the processes in the memory, and you can see back orifice, so immediately you should report, right? Back orifice is kind of, well, things for bad things that bad people can install in your system. So we have some kind of blacklist, and when you scan those objects in the memory and you see them, we immediately report them. Second one, whitelist to, usually malware scanner can have some false alarm, false positive, for example. So you create a whitelist. So whitelist consists of all the exception that should not be reported. So you can eliminate the false positive with whitelist checking. Okay, so how about last method? We process the information written by eagle eye, and the idea is that if you see something abnormal, we report. Abnormal thing can be the modification to the critical places. For example, system call. Usually, system call should point to somewhere fixed in the kernel memory. Now, if you get on the system call and check every system call, now if you see one system call point to somewhere else, not into the known place in the kernel, you report. Because somebody tried to install something in the system call to replace it, right? And so on. You can see something abnormal in other places, like processes, import arrestable, export arrestable, kernel driver, interrupt descriptor table, or TDD table, and so on. So here's the detection model. We have some checking. Every checking can report something that can be malware. But you can see that baseline detection can be optional. Why? Because it's good to have baseline, but in fact, you don't always have baseline. Because maybe you don't know your system is clean or not. So that's optional. Yeah, demo. Yeah, it seems like I talk too fast. So this part I introduce some demo. So you can see that eKimono can really detect some rootkit. You can detect user spy rootkit or kernel rootkit. This one screenshot. In this screenshot, you can see that I run the eKimono scanner against the memory of the virtual machine. And here you can see that those red lines are reported as malware. So in this case, I found I tried to install one keylogger in the virtual machine. And you can see that from outside, you run the scanner, and you can see that the keylogger installed 3 kernel modules, 3 new kernel modules. That's not in the baseline. I see something not in the baseline, so I reported. And after that, I see that this system call, this keylogger modified 3 system call: anti-create key, anti-enumerate key, and anti-open key. And you can see that those system call point to somewhere else, not in the kernel, but to somewhere else. And I can even identify the kernel module and where the kernel module stay in the file system. So You can detect keylogger, kernel-based keylogger. Second one, this photo rootkit. Maybe somebody know. You can see that I run the scanner outside, and you can see that photo rootkit try to hide one process named iExplore.exe. And I detect that because I use a cross view checking here. And I see something not in the cross view, I see something not in one view, but it exists in another view. So I can detect one hidden process. And you can see that PhotoRootkit installed one new kernel module inside the list of the kernel module of the system, which is named MS direct x.sys. It sounds like a DirectX driver from Microsoft, but it's not, because you can see that it's here. Right. You can see the part of the place where they put the kernel driver. And it's not register, it's not in the baseline. It's hidden module and not in baseline. So two method detection, not only one. Vanquish rootkit, it's very popular. You can see that Vanquish rootkit patch many important functions in the service.exe. It patch resist C, close key, create process as user W, create process W, free library. It modifies those important functions because it tries to hide themselves from the memory. So when those functions run, they don't see the vanquish rootkit anymore. And also, it modifies many important functions of the svhost.exe. Break, close key, load library, XW, free library. So I can detect that because the method abnormal modification, abnormal behavior detection. Here, vanquish modify many things. It also modify explore.exe. The same rootkit modify many processes in the memory. They patch many important functions. Okay, so that is those screenshot. And now I show you a real demo, not only screenshot. So here, is this machine I run Zen. And I show you the list on the virtual machine now. You can see, so in my machine I have two virtual machines. Domain 0 is a host virtual machine, and I'm inside domain 0 now, okay? And also my scanner is inside domain 0, in the host virtual machine. And there's one virtual machine named XP3, which has ID 1. And XP is here, which is Windows XP Service Pack 3, latest update. Now, I run my scanner against this virtual machine. So, my scanner name eKimono, and I scan the Zen virtual machine, right? Windows XP, the virtual machine has ID 1. So, I need to tell eKimono that I want to scan the virtual machine, Zen ID 1, okay? Now, I need to tell eKimono which OS this virtual machine run. And in this case, this one run XP Service Pack 3. Okay, very simple. You can see it try to find many things. It look for hidden processes, hidden kernel module, unregistered kernel module, checking export arrest table, system call, IRP hook, imported arrest hook of all the processes in the system. You can see that. Now I can tell you that my virtual machine is clean. So basically it doesn't see anything, but there's some red line. But those are, well, false positive. So for now, just ignore them, okay? So now you can see that my malware scanner run against the virtual machine and it doesn't see anything. It's clean. Now, inside virtual machine, I run one rootkit. And again, we scan to see if you can detect the rootkit or not. Okay. First one. Now I run rootkit, but because actually I don't want to damage my virtual machine, so I run one normal application. But this one behave like rootkit. So if you can detect this one, you can detect the rain rootkit as well. That's the first one. I run this. And everybody knows this, right? Resist monitor from sys internal. This operation can be used to monitor all the activities about resist inside the virtual, inside your system. So this one's very, I think, very familiar to everybody here. Now, I can say that this resist simulator is not rootkit, but it behaves like rootkit. It does many things like rootkit. Now from outside, I run the scanner again. Scanner again. You can see that. Something changed. You can see there are many red lines this time because I run the rootkit. So yeah, here's the result. Yeah, you don't see anything here not anymore, but we scroll up. Sorry, too much. Yeah, yeah. You can see that. We detect one new kernel module. Registry monitor insert a new kernel module named regist71701 into the memory. And registry monitor patch many system code to monitor the registry activities. Anti-close, anti-create key, anti-delete key, and so on. So you can see the rootkit, right? Yeah. Now, let me close this rootkit. I close the registry monitor. So, system is clean now, right? Now let's try to scan again. You can see that even if we close registry monitor, it still keeps the kernel module inside the memory. But the system code is clean now. After registry monitor is closed, it recovers all the system code. You can see the difference? Yeah, that's rootkit, and you can detect that, right? Second demo. Yeah. Now I run Notepad, and you can scan here. Where's Notepad? Yeah, yeah. Here we go. Okay. It's clean, right? Notepad is clean. Now I run another rootkit, and This one is not rootkit, but it behaves like rootkit. This is a monitor, print monitor. And this program modify many important functions in all the processes to try to detect all the printing activities. Now we scan again. You can see that this rootkit installed a new kernel module here. mch in driver.sys initialize in the file system. And now look for the notepad. Come on. Oh, sorry, I need to run notepad. I need to close notepad and run again. Now I run notepad. And when notepad open, it will be modified by the rootkit. Now we scan again. It doesn't patch the already run process. Come on. Okay, where's notepad? It's down in the list of processes. Okay, here we go. You can see this time many functions about printing by notepad were patched by that rootkit. It patched many functions about printing, end page, about documentation, end up, start page, and so on. Because it wants to monitor print activities. Now I close the rootkit and scan again to see if notepad is still infected. You can see that even after I close the rootkit, it still keeps the kernel module in the memory, still over there, right? Now see notepad. Now the rootkit already closed. You can see if notepad is still infected or not. Come on. Yeah, notepad here. Okay, it's clean, right? No more patch imported function because the rootkit, when it closes, it recover on the patches function. So that is our demo. Here's my conclusion. By putting the malware scanner outside the virtual machine, we have many benefits. Zero cost deployment. Malware cannot attack our scanner. We are invisible to malware, and you can disable the malware from outside. Any question?
Time for one or two questions.
I have a question. Do you do any evaluation with the real-world rootkits or real-world application settings to see both true and false positives?
Yeah, there are some of course.
So,
But actually, I can say that I never seen any rootkit that can evade my scanner. So, want to ask about false positive or false negative?
false positives.
No. But you can see that, for example, resist monitor is reported, right?
I mean, for example,
Just false positive, yes. I can say that's just false positive.
I mean, for example, does this mean every time someone wants to print something, this will cause a false positive because this application has a similar behavior?
Yeah. So yeah, I can say that they are false positive. For example, I report that somebody tried to insert some kernel module in the memory and modify many system code like in the resist monitor case. That's not malware, right? But I still report. So you consider that false positive.
Okay.
Can also be seen as some dirty tricks other tools are doing. Any more questions? Then thanks a lot.
One more question?
One more question.
Yeah. Sorry, today I lost my voice, so I didn't perform really well.
I missed the first part, so my question is, Did your scanner run only on the machines, on the host systems mentioned in your slides, or is it possible to run it even on an Hyper-V host?
Hyper-V?
Yep.
Hyper-V is possible. Hyper-V is
It's
doable.
host. Yeah.
Yeah.
Oh, that's fine. That's great.
It doesn't
Thank
work
you.
now, but I can make sure it is that it works.
Yeah, that's great. Thank you
Yeah,
very much.
yeah, thanks. Why? Because Hyper-V provide all the interface I need to access to the memory, to access to receive everything. So the same scanner can work without modifying much. Just build a new plugin for my framework. Yeah.
Okay. Thank you. If there are further questions, maybe you can have some talk outside. Thank you very much.